Hello, my name is Ju Hongmin, and this is joint work with Jungmin Lee, Jiang Ponce, and Minsu Cho. This paper proposes a novel matching network that dynamically composes hypercolumn features for visual correspondence. Visual correspondence is a fundamental computer vision problem with numerous applications, such as object recognition, visual tracking, and 3D reconstruction. In this work, we aim to establish correspondences between images depicting different instances of the same object or same category. Recent approaches to correspondence build on monolithic and static feature representations in the sense that they use a specific set of feature layers and adhere to it regardless of the images to match. However, correspondence is all about precise localization of corresponding positions, which requires visual features at different levels to analyze finer details and larger context in the image. In this work, we introduce a novel dynamic feature composition approach to visual correspondence with trainable layer selection architecture using Gumbel subtomax feature gating. Our main contribution is threefold. We introduce a novel dynamic feature composition approach to visual correspondence that composes features on the fly by selecting a relevant layer conditioned on images to match. A trainable layer selection architecture for hypercolumn composition using Gumbel subtomax feature gating. The proposed method outperforms recent state-of-the-art method on standard benchmarks of semantic correspondence in terms of both accuracy and speed. We now describe the proposed method in 4 steps: multi-layer feature extraction, dynamic layer gating, correlation computation and matching, and training objective. As a feature extractor, we adopt a convolutional neural network pre-trained on a large-scale classification dataset, which is commonly used in most related methods. Given 2 images, the network generates 2 sets of L-intermediate feature blocks. We call the earliest feature blocks base feature blocks. A pair of source and target feature blocks at each layer is passed to its corresponding layer gating module. This module has 2 branches, one for the layer gating and the other for feature transformation. The first branch of each layer gating module takes a pair of feature blocks as an input and performs global average pooling on 2 feature blocks to capture their channel-wise statistics. Those average pooled feature vectors are then added together, and MLP of 2 fully connected layers with ReLU activation takes the vector and predicts a relevance vector for the gating, whose entries indicate the scores for either selecting or skipping the layer. To make the layer gating trainable and effective, we adopt the Gumbel max trick and its continuous relaxation. To encourage the model to increase diversity in layer selection, we add Gumbel noise to the estimated relevance and make the gating decision using argmax. The second branch of the layer gating module takes a pair of feature blocks as an input and transforms each feature vector over all spatial positions while reducing its dimension. This branch is designed to transform the original feature block into a more compact and effective representation for our training objective. Note that if the Gumbel gate chooses to skip the layer, then the feature transformation of the layer can also be ignored, thus reducing the computational cost. During training, we used a straight-through version of the Gumbel subtomax estimator. 4 passes proceed with discrete samples by argmax, whereas backward passes compute gradients of the subtomax relaxation. In the forward pass, the transformed feature pair is simply multiplied by 1 or 0 according to the gate's discrete decision. The output of the gating is a set of selected feature blocks. We construct a hyperimage for each image by concatenating selected feature blocks along channels with upsampling to the size of the base feature blocks. In order to reflect geometric consistency in matching, we adapt probabilistic Hopf-matching algorithm to the hyperimages. The key idea of this algorithm is to reweight appearance similarity by Hopf-based voting to enforce geometric consistency. We propose 2 objectives to train our model using different degrees of supervision: strongly supervised and weakly supervised regimes. In strongly supervised setup, we assume key-point match annotations are given for each training image pair. We define the strongly supervised matching loss as the sum of the crossed entropy values between ground truth and predicted correlation matrices. In weakly supervised setup, we assume that only image-level labels are given for each image pair as either positive or negative. The weakly supervised matching loss is designed to encourage low entropy for positive pairs and high entropy for negative pairs. Please see the paper for more details on these training objectives. Moreover, we add a soft constraint in our training objective to encourage the network to select each layer at a certain rate. This improves training by increasing diversity in layer selection, and, as will be seen in our experiments, allows us to trade off between accuracy and speed in testing. Finally, the training objective of our model is defined as a combination of matching loss and the layer selection loss. As shown in the table, the proposed model clearly sets a new state-of-the-art on both strongly and weakly supervised regimes. In particular, our weakly supervised model shows more reliable transferability compared to strongly supervised models, outperforming both weakly and strongly supervised state-of-the-arts by significant margins on PF reload. Also, we train our model on highly challenging dataset known as SPARE71K and compare it to other recent methods. Our model achieves a huge improvement over the current state-of-the-arts. This plot shows performance and running time of our models trained with different layer selection rates. It shows that smaller selection rates in training lead to faster running time in testing by encouraging the model to select a smaller number of layers at the cost of some accuracy. The selection rate can thus be used for speed-accuracy trade-off. This figure demonstrates category-wise layer selection patterns. Each group of animal, vehicle, and man-made object categories shares its own distinct layer selection patterns. This figure illustrates layer selection frequencies at different layer selection rates. The model with a small rate tends to select the most relevant layers only, while the model with larger rates tends to select more complementary layers. Thank you for watching. Please see the paper or visit our poster session if you have any questions.